we have to look back a bit what we did in the very past. So this club station is existing basically since about 1977 as Delta Kilo Zero Oscar X-ray at different sites, as you can see. We use multi-antenna systems since about the early 1980s. If I say we, I must say I have not been really part of the group until about 2006, but we're always in contact with them. And since 1997, about, I don't know the exact date, we have this mast chuck, which in fact stems from 1964. So it has had its 50th birthday already. An old Mercedes lorry, which weighs 9 tons and allows to set up a mast with a nominal height. So if you build it exactly as it was intended, of 37 meters, we will have slightly varying height, but around this value. So our site, everyone is more or less restricted to the area where he lives. Our site is in the northern Black Forest. Excuse me if on this map of Europe the main part above is missing. And I wanted to show the mountains, and to be honest, there are not so many mountains here in the area. A bit more north, yes, again in Norway. But if you look on the mountains, you see the Alps as a real big mountain there. And then there are those smaller mountains like the Black Forest here, Swabian Alp here, and les Vosges en France, c'est ici. And this Black Forest, this is the southern Black Forest, and this is the northern Black Forest. The northern Black Forest has 2 ridges. We are on the eastern ridge, on the highest peak of the eastern ridge. This peak is called Olo and has a height of 987 meters. It's not a bad QTH, but it has also its disadvantages. The takeoff is not bad. We don't have always negative elevation, like SB0N, for example. But we have one direction where we have a higher mountain on the Splendid of the Western Ridge in our way, by 15 kilometers away. And around there is some elevation close to 0, but most is about minus 0.5 degree. So takeoff is good. We can go there. That's the main part often, because many points are not accessible at all to build up a big contest station. And we even have, since some time, line power available. They're a bit limited, so for the smaller contest it's okay. For the bigger contest we still use a generator. The disadvantage, yeah, you can just look on this photo and then you see the problem. The problem consists of trees. These trees have a height, depending on if it's south or north, around 20 meters, some a bit higher. Luckily we had a big storm in 1999, which has taken away a big part of the trees, but this is now 18 years ago and they are growing again. And so this is one of our big problems, that we need a high tower, a high mast to come over the trees with our antennas. This is a map that had been generated by several old men, among them S53 Whiskey Robbie, who is now also responsible for the IU contests and IU contest task force or whatever it is. He has generated this from logs sent into the IU contests, and it shows the distribution of active stations. In this case, stations which are active more than 18 hours, but I think if you would take another criterion, it wouldn't look much different. And you see, if you look, where are we? We are somewhere here, so quite in the center of the activity. If you look where we are at the moment, yeah, here it's not too bad, but you see to the north, yeah, it's difficult. To the west, you have not much, so you're at the edge of the activity, at the outskirts. Or I have another example of a French station. I want to show it in the map already, which is down here. They are in the same situation. So it depends where you are, if you want to know how to win. If you're at the edge of this activity zone, then you have the disadvantage that you have stations only in a limited angle, and so it's less stations what you can reach normally, and you have to hope to wait for special propagations, for unusual propagation conditions. but then you can win with a very good result. So example 5 Papa 5 Tango in 2013 with 900 QSOs and an average of 520 kilometer per QSO. I have another example. This was not an IRU contest, but a sub-regional in, I didn't translate from French, I see, in July 2013. This was Tango Mike 7 Golf. They had only 729 QSOs, but they had 828 kilometer average because they worked into Norway and into Denmark and into Sweden. There was a big duct, and they worked into UK and they worked into Germany and everywhere. And they had 600,000, more than 600,000 points. That's something I think we will never achieve from our centered side. If we're in the center of the activity as we are, we have the advantage that we don't need special propagation conditions. I did not want to say they may even be harmful to us, but I think it's easier, it's better for us to win without propagation conditions, because otherwise we have to compete with difficult situations, and often we cannot profit from these propagation conditions because there are not so many stations out there where they go. So our example from the last year, 1121 QSOs, which is much more than this, but less average, 443, and so we ended around 500,000 points, which was very good, our best result ever, very good result for us. If you are thinking about how to build your station, especially how to build your antennas, that is one of the most important points. If you're at the edge of the activity, you will have 3 or 4 antennas, something like this, which is completely sufficient because you have to cover only a certain angle, and then perhaps for some scatzer, so you can turn one antenna away or around. That's not the problem. If you are like us in the center of the activity, you don't know where you have to call to. You have to call to all directions. You need an omnidirectional transmit antenna and also enough gain, which means, in fact, you need more antennas, more PAs, more of everything. It's like this. So we had over the time between 7 and 11 antenna systems typically, others 4 to 6 or 5 examples from other stations, so more than if you are away. Okay, now come to our specific example with all these trees. We cannot really afford to set up 2 or 3 towers. So one big tower is the best compromise. So we have to put all antennas on a single tower. We could try to put all antennas on top of the tower, which would be something big and difficult to manage, perhaps difficult to set up also. As the tower is high enough, with 37 meters against 20 something for the trees, we can also put antennas side of the tower, and we can even combine both, and that's in the end what we do. We have a cable length of about 40 meters, which is more than many other stations which have a lower mast and close to the station. So yeah, we use half-inch self-flex cable for the transmitter, and we have all the transmit-receive switches and all the preamp things on the tower, which has a problem that they should not fail. Otherwise, we have a problem in 30-meter height on the tower. So our antenna in the years 2006 and 2012, that was a time when we were quite active and had mostly the same system. So we had 2 times 17 element on top, 3rd floor. We had 6 single 9 element Yagis around on the 2nd floor, you could say. And then we had on the ground floor, wherever in the basement, we had additional antenna, especially for the east, because there was high activity in Oscar Kilo, Oscar Mexico, that we wanted to cover this area, especially with more gain and more power. So, and used 4 times 6 in one case, also 8 times 6, and there were other configurations slightly different, but more or less the same. Yes, and all these antennas up here were on one single tube and had one single rotator. So they are turned all together. That was the old system, which was quite successful over the years. Looks a bit like this here. I have drawn by mistake one antenna too much, but you turn the whole system. You turn this whole system around. This allowed us to measure the diagram of this antenna system on top. consisting of the 2x17 in the main direction. You can see them here easily. 2x17, and then other antennas. One here, one here, one here, one here. Starts here, here, here. These are the other 6 around. The difference stems from several factors. One is that the 4x17 also has more power. 2x17 has also more power. So it's not to be expected that they are all at the same level. But what you see is that we have deep holes in the diagram. Something like this going down here. Which is not good. It's not so bad because we turn the whole array, so all the diagram shifts around when we turn the array, so we fill up the holes at other times. But it's far from being omnidirectional, one has to say. This measurement has been done from DR9A QTH to my QTH. And one of the few contests, we had a little time before the contest because everything worked already. It was in the November contest, and so I was at home at that time. And so we did this measurement. The results with this antenna system and from this area, from this era, are 2006, 2012. Mostly in the same area point-wise, so 419, 416, 415, 422, 410. But going down, maybe this was a bad year, and now 2012, only 390. Resulting in first or second place, something like this. But you can also see that the number of QSOs is considerably going down over the years. So we started with nearly 1,100, we had 1,100 claim score QSOs. And at the end it was less than 1,000. While new tools like KST and so came up and allowed more scats and longer range and all this, this compensated a bit the loss in active stations, but yeah, the activity was going down. But you can say we were a bit above 400, 410 to 420,000 points around typically, if we leave aside the 2012 result. Then we had some creative break, or whatever you want to call it. So in 2013 to 14 and 15, we were at QV on 2 meter in VUSHF. We restarted 2016, and Helmut DK8SG, who is the main responsible for the 2 meter station, decided he wants to try the more is better approach. So as many antennas as possible. So he left the old system up on top with all these 6 single element Yagis and the 2x17, and he added 2 more of these 4x6 around the mast. So there are 3 groups, 1, 2, and the third to the back. And then he still had 2 antennas, so he has put another 2 antennas to the rear area to cover this area with fixed antennas. So at the end, we ended at 11 systems, nearly all directions double covered by a small antenna on top and a larger one down. And yeah, the result was not so good. It was not bad for the fact that we had to re-establish after some years with operating practice and setting up and everything. But finally, those 6 9-element Yagis here on top have nearly never been used on RX, and I think the influence on TX was also not the best, so we should have removed them already then. And also this double coverage, as we can see, causes more problems than it helps. The result was...
Do you use the 9 elements as a single Yagi or...
Yes, as a single Yagi. No, as a single Yagi. Every 11 systems, every one can be switched on RX as a single system, yes.
Okay.
Yes. The result was in line with the others, I would say. 410,000 points, 942 QSOs, second place after Oscar Echo 1 Whiskey. So you could easily see this may have not have been the good way to do it. It's very complicated. Just aggregating antennas is not the right way to do it. And so we had to start from the ground, from a green situation, from nothing installed. So what should we build for 2017? The idea is clear. We want to have an omnidirectional transmitter. It should work as good as possible. And we want to have directional RX because, again, also to get away of QRM. But we would prefer to cover the 360 degree also on RX without turning antennas, so that we can just switch because this helps not to overhear something. This helps to speed up the operating time and so on. So we started from the ground, thinking what can be done, then doing some simulations, and finally built the stuff. We did not want to start really from new because we had already these 3 groups of 4x6 elements, which also worked quite nicely. So the basic idea was to use these antennas and build more of them. This 4x6 element there's several reasons why we use this antenna. One is we have to mount all our antennas in front of the tower, so that they are supported only at the back end, so we can't use too long Yagis. They are 2.6 meter long. You buy your aluminium tubing in the length of 6 meters, so if you cut it in the center, there are 3 meter, and then it's a good idea to have an antenna which is 2.6 meter and still has 40 centimeter at the end for mechanical support. So reasons like this are easy to handle and to store and everything, and they worked quite well. So we stayed with these antennas. They achieve about 18 dB isotropic gain, and horizontal beam widths of 50 degrees. The side lobes are quite well suppressed, so which is also a good idea if you try to aggregate quite a lot of them. The basic diagram is already clear. So of these stacks of 4x6, we would need, you can easily calculate 360 through 50. If you do this, you end at 7. 7 is maybe not an ideal number for making a mechanical construction, so we said either 6 or 8. 6 or 8 stacks is what we would need for our 360-degree coverage. Okay, now I want to start with the simulations. The simulations are based on a NAC simulation of this antenna array with the original data. And then I took this data generated by NAC, which is amplitude phase of the generated electrical and magnetic field. And then I just superpositioned the antennas I have. So if I have these 2 antennas, for example, I used the original NAC result into this direction and the NAC result in the back direction with an offset according to the distance, and made some MATLAB scripts to generate diagrams to investigate the situation a bit. And I started with only 4, which is more a situation for other stations which set up 4 masts maybe in 4 directions. Let's say DR9A, for example, our strongest competitor in the moment. Their antenna system looks more or less like this. Note these antennas, but this is not important. And what you can see now is if I vary the radius, if I start theoretically at a radius of 0, which is cannot really be realized, but you can calculate it this way, and then I increase the radius up to 20 wavelengths, which is 40 meters. So if you have a real big-sized area, what happens then? So we can have a look here, and you see the radius here, and you see this diagram, which is calculated the way as I did. It is not exact, not 100% exact, because the coupling between the antennas, the electric coupling between the antennas through the field is neglected, but it gives quite good results to have an idea of what happens. And you see it's not bad. These 4 antennas keep their basic diagram. There is some interference between them, so little change in the diagram, but nothing that is really a big deal. One has to say, I just let it run once again, if I can. One has to say the scale here, how I did it, is linear in field strength. So a factor of 2 means 6 dB. This is 6 dB, or this is 6 dB, or this is about 3 dB. So that you have an idea what this means. It's always the same scale in all these simulations, linear and field strength. Not linear in power, not logarithmic in power, not linear in dB, linear in field strength. Okay, so for the 4 dimension. Now let's assume we are DR9FF, and now we want to turn our antenna. I have assumed a radius of 20 meter, so from the center point 20 meter to each of the masts, and now we turn this antenna around, and look what happens. And you see what happens. when those antennas are pointing in more or less the same direction, or when they start to have a common area, a common angle area where they radiate, you get strong interference between these antennas, and you can observe that the point of the maximum and minimum does not shift much. You turn the antenna, so you still have some directions. If you just turn one antenna, you still have some directions where you cannot produce a good signal. You had to turn all the antennas at the same time. Then you would avoid this super precision, but usually this is not done. So now we don't want to cover just 4 directions, we want to cover 360 degrees. So let's look what 6 Yagis do. Same game, I start at a radius of nearly 0 and go up, and go up. And you see what happens with the diagram of the 6 Yagis if you go up. If you think you place 6 antenna masts around the center and have one of these diagrams, one of these antenna arrays on each of the masts, and you see the same problem that we have already seen on the 4 Yagis. If you start to turn one antenna, comes up again in this area where they overlap. So you see the original 6 directions of the Yagi, but in the overlap region, it is not a good omnidirectional antenna unless you keep the radius very small. If you keep the radius very small, I will try. Yeah, something like this perhaps. It was already a bit too much, but you see then, okay, you avoid this interference. So what you have to do is to place the antennas close together, which is very good for us because we have one tower. You want to have all antennas on one tower. So, but yeah, we can also turn one antenna. Maybe this is not so interesting. It doesn't give really new experience, but it shows the same problem. If the overlapping region even increases, then you see you have even more interference in this area. It's not a good idea. This is again a 20-meter radius, not our situation, but the situation of our competitors. So once again with 8 antennas, same game. Not too much. Good if the radius is small, and if you increase the radius only 5 meter, 6 meter, 7 meter, 8 meter, 9, 10, 11, 12, 13, 14, you see, it looks interesting, I would say. It's just interesting, but not very useful. So I think we don't have to end this to the end. Okay, so we found out it is good that in our situation, if we keep these antennas on a quite small distance, and a distance of 1.4, a radius of 1.4 meter would fit most of our requirements. We can't choose this arbitrarily because we have to mount the antennas and we have to take them up, and they should not be too far out and not too far in, and there's mechanical reasons for that, and there's electrical reason, but that fits quite well at 1.4 meter. And so we get the diagram, and I turn one antenna, so we have a quite nice omnidirectional diagram. Oops, one too much. And if I turn the right antenna now up and now down, okay, this omnidirectional antenna is changed, diagram is changed, but it's still on an acceptable level, so one could turn the antenna really to optimize for RX, but later we found out we don't need it. The first installation we did was with rotators, but no one has ever used them. So now we have rotators. Okay, this was nice calculation, assuming that all these 8 arrays of antennas have the same phase in reception like in transmission, but we're speaking here especially about the transmission side, where all antennas should transmit at the same time. But this means that we either have to feed all the antennas by one single amplifier, maybe a bit of big amplifier. First we had to build one, then we had to build a second one because the first one can fail. And maybe it's not the ideal way, especially as we already had some equipment naturally. And, so if we do it the conventional way, I would say we place a separate amplifier to each antenna, then yeah, we run into new problems because the phase between these antennas will be undefined in the first moment if we don't do anything. And so I made some simulations with randomly chosen phase on each antenna. And made quite some simulations, I think 100 or something like this, and played them now as an animation. So what you see is if you randomly choose the phase in one way, then the diagram is calculated, then another phase drawing in the lottery, and then again the diagram is calculated, and you see how this diagram can change. And it's far from an omnidirectional antenna. So that happens when you build these 8 antenna groups and just feed them somehow by the same power on each antenna with undefined phase. If you're lucky, you win. If you're not lucky, you may have once again very deep holes and they will never move. So this will not be a very good solution. So one has to do something on the phase 2. Okay, let's assume we are able to reduce the phase variation to a range of 180 degrees. If you look, you will see it's not much better. It's a little better. There are more nicer diagrams and less ugly ones, but the ugly ones are still very ugly. Not really. Okay, so we have to be better. Let's assume we can reduce the phase variation to 90 degrees. 90 degrees means it's no more possible that 2 antennas are 180 degrees out of phase, which would produce a deep zero in between. But they are now restricted to a maximum of 90 degrees, so one could already think, and it's in fact like this, that the diagram looks better. It's not really what we perhaps expect from an omnidirectional antenna, but we are talking here about 3 dB, about something. This is 3 dB, but this is 6 dB. So you have an idea. It's not ideal, but okay, one could say, yeah, why not? It's not so bad. But one can try to make it better. So if we go down to 45 degrees, then as long as we are not a broadcast station which have to provide a very accurate diagram, I think for our ham radio purposes, we can say this is a good omnidirectional antenna. We don't have to adjust the phase more precisely. So this is finally what we have focused on. 8 arrays, 4x6, 1.4 meter radius to the center, and phase is 245 degrees. So now, if you make a drawing, you will find out easily that the reflectors of the antennas nearly touch each other if you place them on a radius of 1.5 and 1.4 meter. This will cause some difference in electrical properties for sure, and will detune the reflectors. And also it's mechanically difficult if you have to place those and have to set them up. You can touch it, you can destroy something, and so we decided to change this configuration a bit, not really a lot, by using 2 subsystems of 4 arrays each, and the second one, and put them in an offset of half the stacking distance, which is 2.5 meters, so 1.2 meter per offset. Finally, we ended at 80 centimeter, but in offset enough that those reflectors do not couple anymore to the others, and that also the mechanical problems are gone. And so that is the result. On the right side, you see these two subsystems here, and also in this direction, and the other 45 degree turned, and in a vertical offset with this radius 8 times 4 times 6 around this mast. And for the total antenna, I did again a full neck simulation, and yes, the pattern is not completely ideal, but I think you can say it's good enough. It's about 1 dB variation around the full angle. While what you can see is the main direction of the antenna is 0 degree. The maximums are not in the main directions of the antennas because they overlap so much. The maximums are where 2 antennas contribute, 2 arrays contribute between the main direction, between the beam width of the single systems. There is a maximum. Yes, we have still a free top of the mast, so we should perhaps put something on. It's not so easy to find something that can beat these antennas really, because you want to have at least 3, maybe 4 or 5 dB more gain, otherwise you would not take an extra antenna in this direction. And so it starts to become bigger and bigger, the system mechanically more difficult. So we ended at 4 times 17 element M2, 10 meter long antennas, stacked horizontally, the way that the horizontal diagram is as clean as possible, so that this is the side lobe and the 0 is coming from the stacking distance. So we tried to put the first side lobe as much as possible, while the vertical stacking is a bit higher, more gain oriented. And we ended at simulated gain of 22.5 dB, so this is a bit more than 4 dB more, 18.2 was the figure for the 4 times 6. So one could say, okay, it can help in situations, special situations. Also helps to remove a bit the QMary from other stations to the narrow main loop. So in some cases it helps, but it causes also a lot of work to set it up. So I'm not sure if this is really necessary, or we should perhaps leave it off and just use the other antennas. Now a bit more about the station, schematic of the station. You see these 8 antennas. I don't talk about the 9, it's extra, but just these 8. These 8 antennas here. We have TR switches and a preamp matrix, which I want to show in detail still. Maybe some amplifiers, you never know. And then we have 2 operator positions, identical, each one with the same radio. We use a crystal filter bank in the IF, so that on each frequency we can switch in crystal filters to remove, especially on our TX signal, noise, and also perhaps strong signals from other stations and the RX. We have this Javonic transverter, which we use since a long time from S5, which works quite nice, and has already 2 receive channels. Yeah, and a relay that allows blocks the other operator, the other transceiver, allows each one to transmit first come, first served. That's all, and then the operators have access to a special RX antenna control, which works on these field objects as we still see.
Question: why did you use 14 MHz IF?
Because first, because the Javonic has 14 MHz IF. Second, because at that time when the Javonic was developed, they developed it for the FT1000 especially, and it had better properties on 14 than on 28 MHz, which is not true for all radios. And so yes, this was historically mostly. I think still many radios are better on 14, but you can't generalize. So yeah. In our case, it's historically. We started with FT1000 Javonic, and at that time this was really the better option. Yes, I told you we have to adjust the phase of the transmitters, so we have to measure it. In our mask box, from the output of the mask box to the antennas, we can control the cable length very well. We just use identical cables; they are not very long, so we guarantee the phasing by the cable length. But before, we could do this also. We could measure all the cables and number them and exactly use them in the way, but assume that the power amplifier fails and you want to replace it by another one, then the phasing is gone. So it's always better if you are really able to measure the phase on site. And for that we have one of these Ericsson directional couplers, you all know, I think. We have very special ones which have a 716 connector on one side and the Russian SR50 connector on the other side, which we did ourselves, modified it this way so that we can directly place a Russian REW14 relay on each. And we have this 8 times. And then we take out forward power of this directional coupler. And from one antenna, from the antenna 1, we go to one channel of a simple phase detector. And from the other channels, from antenna 2 to 7, we can switch over an SMA relay 7 to 1. to the other channel. Naturally, the cable length or the phase delay on all these paths are the same, are measured to be the same. And so we can measure with this 80H302 during transmission, even during SSB transmission, you can do this anytime. We can measure the phase difference between two antennas, between antenna 1 and one of the others. So all we need is an adjustment possibility, yes?
Because where the phase shift, where we can shift the phase.
This is not included here. This is we can do this. I will talk about it. In the moment, I talk what is in the mask box, in this preamp box. So maybe to give you more insight, I talk about the interior of this box. So this was part of the interior of this box, and this is another part of it. This is the RX path. So we come here from the RX side of the coaxial relay, the 8 antennas. We have 8 times the same unit consisting of a helix filter against broadcast stations. SPF 5189 as a preamp, then a splitter 1x2, 2 times AH1 as a post amp. Then we have on-off switches, electronic on-off switches with quite high isolation. So we use 2 cascaded also to allow to be matched from all sides always. And we can switch on and off each channel. So we have 16 channels in total. And from each preamp, the first channel, the upper channel, goes here from the first, here from the second, from the third, and until the 8th. So we have 8 inputs into a combiner, into an 8x1 combiner, which combines these signals if the switches are on. We can switch on and off separately each of these switches, so we can combine any antennas we want in the RX. And we have a second RX channel for the second operator, which works the same, completely identical. Again, post amplifiers are not AH1 but AH102, but it's not really important. They are necessary to compensate for this splitter loss, and we do not have any preamp, even not the built-in preamp from the Javonic interstation down. We go directly to bypass filter and mixer of this transverter. We have all preamplification up in the box. So the result is that both operators can listen whatever they want independently of each other, any arbitrary combination of antennas. And this way you can even try to synthesize your antenna diagrams, and we need this to use this method. And we found out it's no more necessary to turn the antennas ever. Only the 4x17 in a very difficult situation can be called for help. To show this a bit, this is antenna 1, diagram of antenna 1 and of antenna 2. Once again in this linear in field strength scale, so 2 to 4 is 6 dB, 2 to 8 is 12 dB, and so on. Antenna 1 and antenna 2, and if now I activate both switches on antenna 1 and 2 and combine them, I get a diagram that looks like this, like the lower diagram. So we have a diagram which is a bit wider than those. It has nearly the same gain. You see we achieve here nearly the same gain, and which is intermediate to these antenna diagrams. And we can do this with any other antennas too. So if we switch on 2 neighboring antennas, we have precision in between them. So we have, in fact, 16 positions. You can see this again in an animated system where you see how we can turn the antenna. You see here which antennas are selected, and how the diagram, how the antenna then works and changes. So we can fully electronically rotate our antennas without moving anything, and that's the way how we do it now. Yeah, sure. If I have enough time, because the problem is my time is more or less over already. Yeah. So if you want to see it together, all diagrams written with the other you see, we cover with less than 1 dB variation the full 360 degree by these 16 switch positions. We can also synthesize other diagrams like circle or full circle, full omnidirectional, losing gain, getting more QRM, but maybe in the first hour it might be a good idea to hear more, just to reduce the time for the single QSO, so this is also possible. Okay, now I talked a lot about theory. I have 2 minutes, maybe I get a bit more. If you're interested. Okay, to talk about the realization. It's just a lot of work. I don't want, it's not necessary to comment the pictures too much. This is, for example, the dipole box. We built all our antennas ourselves, where we have used Teflon coax and the closed box to have reliable system. This is the preamp box, 60 × 30 centimeter with 7/16 connectors up here. This is the downside of the preamp box. We use only 7/16 just because they are more field reliable than N. They don't break so fast. This is a view inside. I think this is something I should talk a bit. 8 of these preamplifiers here with each 2 output channels. Then 2 of these 8x1 combiners, 2 post amplifiers. This is part of the power supply. So you see this is the RX part of this box, of this mask box. Some pictures of the preamplifiers, also homemade. And this is the lower part of the box where you see the Ericsson directional couplers, and then REW13 relay, and transmit receive switches, and there are 4 of them, and 2 of them stacked horizontally. This is this 7x1 SMA relay, and here the phase measuring unit. This was during the test of the phase measuring unit when I made this photo. And now coming back to the question you had before, how to adjust the phase. You see, we built these simple phase stretches consisting of really simple switches, mechanical switches, and line lengths of half wavelengths, quarter wavelengths, and 1/8 of a wavelength, so that we can shift with this one by 45 degree, with this one by 90 degree, and with this one by 180 degree. And yes, at a certain stage in our TX distribution unit, we have separately for each antenna one of these phase stretches, and this is done before the contest, and we transmit on all antennas, and then we have this portable indicator which gives us the voltage for the phase difference, where you can read the phase, and then we minimize this phase difference by changing these switches here. And it's quite reproducible if we set it up a second time and use the same cables. We don't have to optimize it, only if we change something. What can happen sometimes? Yes, this preamp box is a bit bigger than preamp boxes usually are. And cost also quite some work. It's heavy to put it up, but yeah, everything is still possible. It has survived now several contests. We had it in September last year. We had it the first time. We had it in November and in May. So it has been used 3 times. The rotation, original rotator control, now visualization of the antenna configuration is done by such an Android tablet, which gives us the information, and we have something like a mouse with a rotational optical encoder where we can select the antennas also very quickly. You can turn around and listen, is there something? You can change some configurations. If you look on this Android tablet, there is here the possibility to change different antenna configurations, what you want to switch with your switches, and you also get digital indication of the direction of these antennas. You have an additional indication for the 4x17, which you can turn around, so that the operators can also see what the other does. That is important, that the first operator with the yellow can see what does the second operator do in the moment, in which direction does he listen, so they can, without talking too much, they can cooperate. The result this year, if you look there, I would say, yeah, there may be some potential for Oscar Zulu, 11 stations, and Sugar Mike, 6 stations. heard of these 6, maybe 3 are located in JO65 Mexico Juliet, so we would like to have more locators from there. So our main directions, apart from Germany, national HLA France, 176, is Italy, I have to go to these numbers, 177, France, Italy, 121, then comes Czech Republic, 112, then comes England, 50, then comes Netherlands, here Netherlands, 47, and then already Poland, 43, and the rest you can, the rest is 20, 30 stations, something like this, not really much. That is our main customers. If we compare the results, we can see that this new system really put us a step forward. We could increase our points from around 410 before to nearly 500. And it looks like this is reproducible, as in May now we had 430 in the May contest this year. And also the QSO number went up to a number which we did not have before, which is quite a nice result. So for the conclusion, last year we invested a lot of work into 144 megahertz and tried to make it right the first time. So not optimize existing systems, but build something completely new. This was quite a lot of work, not only the thinking and the design, but also just to build everything and to get it ready more or less 2 days before the contest, like usual. We took part in 4 contests. In May and July we did not have the full system, but we tried parts of it. From September we had the full system, as I have shown here. And as you see, we have achieved about 20% increase in points over our former results, and also for the first time in our experience, 500,000 points claim score, which had been reduced to 497. Okay. Maybe this year we can get 3,000 points more, maybe from Sweden or from Denmark, or maybe even from Norway. If you are very on the south coast, it should work. And so we hope that we can cross this border then